Okay, for this video I'd like to talk about molecules that do not obey the octet rule. And the octet rule is the rule that each atom in the molecule will have 8 electrons in its outer shell, other than hydrogen, which prefers to have 2. There are some structures we find that don't obey that rule, and there are 3 things we're going to talk about. We're going to talk about expanded octet, which is the next video, and then here we're going to talk about electron deficient molecules, but the first thing I want to talk about, and it's a little out of order from the book, are odd electron atoms. And I'm going to talk about this first because you won't be expected to draw these on the test. So odd electron atoms are sometimes called free radicals. And so instead of having like 8, 12, 14, 20 electrons, when you do the math, and an example is NO2, when you do the math and you add up the electrons, you're going to have an odd number. So like nitrogen has 5 electrons. Each oxygen has 6, so that's 5 and 12, we get 17 electrons. Now the book shows 2 of the possible resonance structures for NO2, and what you find is that in order to get 17 electrons, you're going to have one atom that's not going to have a pair. It's going to have a single electron somewhere, and that makes it an odd electron atom, and they're also called free radicals. So here are 2 resonance structures that they show you in the book. So if we count it up, let's use this one for example. We've got 2, 4, 6, 8, 10, 12, 14, 16, and then a single electron makes 17. It turns out that this appears to be the more important structure because of the way that NO2 reacts with another NO2 molecule. But that's just a little side note. Now let's look at over here. I've got 2 examples of atoms that are going to be what we call electron deficient, meaning that the central atom is not going to have 8 electrons around it. And we'll find out that's for reasons of what we call formal charge, which we'll get to a little bit later when we study for the final, the idea of formal charge, which is a method for picking the most likely Lewis structure. And so the first one, let's look at this, is BeCl2, and it is an example where we've got a central atom from group 2A. And if you have a central atom from group 2A, one of the rules you can remember is it's going to form 2 bonds. It's going to tend to form 2 bonds. So, well, first let's just add up our electrons. So beryllium, we have 1 atom. It has 2 outer shell electrons, so that's 2 electrons. We have 2 chlorines. Each of those has 7 outer shell electrons, so we have 14 there. And so we can have 16 electrons in our structure. Let's put beryllium in the center. It is definitely, in this case, the most electropositive. And let's put our chlorines on the outside. And let's just give them each a bond to connect them. So that's a pair of electrons, pair of electrons. Now, what you're going to do is, if your central atom comes from group 2A, we're not going to give it an octet. We're going to leave it just with 2 bonds. But we will give the chlorines, the other atoms involved in this, an octet, like that. And so let's count our outer shell electrons. We've got 2, 4, 6, 8, 10, 12, 14, 16 outer shell electrons, so we have the correct number. So this is electron deficient, and just remember it's going to be atoms from group 2A, particularly the ones at the top of group 2A, that are going to do this. So look for like beryllium or magnesium in examples. And so just leave it like that. It's stable like that. Okay, the next one is an example where we've got an atom from group 3A. So like boron, aluminum, gallium. And what's going to happen here is this atom is only going to form 3 bonds. And again, for reasons of formal charge, that is more stable. But let's just go ahead and count up electrons. So we have 1 boron atom. It has 3 outer shell electrons. So that's 3 electrons to deal with. We have 3 fluorine atoms, each with 7 outer shell electrons, and so that's 21 to deal with. So we have a total of 24 electrons to draw in our structure. And so, well, let's put boron in the center. It would be the most electropositive, and what we're going to do is, if my atom comes from group 3A, so boron and aluminum in particular, I'm not going to try to give them octet. I'm just going to give them 3 bonds, 3 pairs of bonding electrons. And then I'll go ahead and give the fluorines their octet. like that, and I'm going to count. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I have the correct number of electrons. So this is an example of a molecule that is electron deficient because the central atom does not have 8 electrons around it. So remember, if you're from group 2A, you're going to form 2 bonds, be electron deficient. Don't try to make double bonds out of that. You could make a structure like that, but it's not the structure we're looking for. And then we've got atoms from group 3A, like boron, aluminum. They're going to form 3 bonds. Okay. Next time we'll talk about expanded octet.